what we have is this. We have sigma 2, sigma 1. And our previous problem, as we stated that we take about approximately the same distance from your origin in a ductile problem. And between this first quadrant, between sigma 1, sigma 2, we make a box. Between sigma 2 and sigma 1, same thing, makes a box. And how the previous problem, what's known as Tresca. Tresca looks like this. This is our Tresca. Tresca came from your chapter 6.2, chapter 6.2.1. That's this is a previous. This is previous lecture. We talked about Tresca. Then, what is a von Mises we're dealing with? Von Mises makes shape looks like this. So, order point, basically we connect. Not very good, so I'm going to. Okay. Oops. One more time. Okay, I connected. And Tresca looks really difficult if you look at this part. So I'm gonna. Why don't I just change this just a little bit? I'll just go ahead and draw Tresca from this way. Tresca is inside this one right here. So this is Tresca, and outside. Outside is the one we just studied. This is the von Mises, chapter 6.2.2, and this is the current lecture. So this again, this is what's known as your failure envelope, and failure envelope looks something like this. And in fact, I did make some. For copy and scan literature, I want to go ahead and show this to you. Oh, next page right here. So you can see Tresca written here and von Mises written outside, and that's how it is. And with that, I want to move on to the next case where the system is a non-principal system. So this one, case number 2. So how did I write the first one? Case 1 principal system. Okay, so here is the case 2, and case 2 is non-principal system. And in a non-principal system, simple explanation for that part, it's simply if x and y are not chosen to be parallel to the principal direction. So that's what you mean by non-principal direction, non-principal system. So let's think about principal. Non-principal means you don't replace sigma xy with a 1 or 2. You just as is x and y. So if you do this J2 expression, that's 1 over 3 times sigma von Mises square. Yeah, that's the same as 1 over 6 times what's the square we have? We have sigma xx minus sigma yy square plus sigma xx square plus sigma yy square plus 6 times tau xy and the square of the term. We have this term. And you have, okay, so you have a bunch of interesting things. You have the sigma xx, this part is a square term, so you have to somehow simplify. So how about let's go ahead and write only this part. 1 over 3 sigma von Mises square, and that equals 1 over 6. And you have, let's expand this expression, sigma xx square minus 2 sigma xx plus sigma yy square plus sigma xx square plus sigma yy square plus 6 tau xy, okay, square. That's pretty good. And how about let's multiply both sides by 3. So instead of saying 1 over 3 or 1 over 6, let's multiply both sides by 3. And if you do this, obviously this becomes 1. And this becomes 1, this is 2. And if you, let's continue. So sigma von Mises square equals 1 over 2. And this inside you have 2 sigma xx, so 2 sigma xx square. And sigma yy, we have 2 of those, so plus 2 sigma yy square. And how about sigma xx? I'm forgetting something here. Sorry about that. This part right here. 2 sigma xx sigma yy plus sigma yy square. Sorry about that. So with this, we have 2 sigma xx square plus 2 sigma yy. Then you have negative 2 sigma xx sigma yy. And you have finally your tau part plus 6 tau xy square. And we have 2 in front, so how about let's 1, this is 1, this is 1, and this is 3. So your von Mises stress, in fact, I like to go ahead and take a square root of this one already to get rid of this square term. Von Mises equals, and I'm also not writing plus minus sign because usually we only take the plus sign. So square root of simply sigma xx square plus sigma yy square minus sigma xx sigma yy plus 3 tau xy square. So this is the value of the von Mises stress. More general case because it doesn't have a 1 or 2. And this is a 2-dimensional version of your von Mises stress. So how about 3-dimensional case? Let's go ahead and write the 3-dimensional next page right here.